Okay, this week we're going to talk about normal distributions. And I have a little bit of a cold, so I apologize. Hope you can hear me okay. These notes go along with the PowerPoint, so you can kind of click through that. It shows you different pictures and stuff too. So I'm just going to kind of quickly fill in the blanks and then explain the examples. So for a normal distribution, this is what a normal distribution looks like. It is bell-shaped with the highest point over the mean mu. And like I said, if you click through on the PowerPoint, you will see some of the pictures for it. It is symmetrical. About the vertical line through mu, it's supposed to be a C, symmetrical, and the curve approaches the horizontal axis but never touches or crosses it. So the empirical rule that goes with normal distributions, it only works on normal distributions. We kind of hinted around at normal distributions before when we were doing the total points scored in the Super Bowl, when I did a standard deviation example. So that was sort of hinting around at normal distributions. I said we'd talk about it again later. So if you look at the PowerPoint, there is a nice picture on a couple slides about the empirical rule. It says approximately 68% of your data values are within one standard deviation. Approximately 95% is within 2 standard deviations of your mean, and almost all, so 99.7%, is within 3 standard deviations. So if you look on the PowerPoint here, I'll show it to you real quick. So it kind of shows you, here's your means in the middle. This is if you go plus a standard deviation, plus 2 standard deviations, plus 3 standard deviations, and then if you go down by the same. 68% is within 1, 95 within 2, and almost all of it's within 3. So for an example here, you have the life of a particular type of light bulb is normally distributed. Anytime you read these problems and it talks about something, I generally will draw a picture just because it usually will help figure out what you're trying to do. It says normally distributed with a mean of 1100. So when I'm reading, I also mark my mu and sigma, just so then you don't have to go back and read again and try to find it. And a standard deviation of 100. So there's sigma. What is the probability that a light bulb of this type will last between 1,000 and 1,200 hours? So you stick your mean in the middle for a normal distribution. So here's our mean. That's 1100. If we go plus a standard deviation, 1 above the mean, 1100 plus 100 gives us 1200. And you can do another one if you want to. Go another 100 up. So 2 standard deviations would be 1300. If we go 1 standard deviation below the mean, 1100 minus 100 is 1000. And if you want to go another one, you can do 900. Usually you'll see 3 standard deviations above and below marked on a graph, especially in textbooks, but I don't draw the best graph because these are supposed to be symmetrical, but mine's usually a little bit off, but that's okay. So you want to know what's the probability that a light bulb will last between 1,000, which is here, and 1,200, which is here. That is within, these numbers are within 1 standard deviation. I'm going to abbreviate here, of your mean. It's plus 1 standard deviation minus 1 standard deviation. So you want to know what is this area. That's the same as the probability. So using the empirical rule, within 1, we have it up here, that would be 68%. If it had said between 900 and 1300, we would have used the fact that it's within 2 and said 95%. So that's just an empirical rule example. Now you do have what's called the standard normal distribution. So any normal distribution you can draw and put your data values down here. Your standard normal distribution will always have a mean of 0 and a standard deviation of 1. All of your x values are your data values. So like here, our x values would be 1,000, 1,200, any value it asks about. If you wanted to do 1150 or whatever, all x values are converted to what you call a z-score using the formula x, your data value, minus your mean, divided by your standard deviation. The z-score tells the number of standard deviations between the original measurement and the mean. And then what happens is when you do that, the areas under the curve, it can be any normal curve, and you can switch it to a standard normal distribution, standard normal curve. The areas will be equal. So if you look here at the picture, so this case, this is any normal curve. You have mu, and then you do mu plus sigma. You can't see it over the arrow, but mu minus sigma. When you switch to standard normal, your mean's always 0. You got 1, 2, 3. If you go 1, 2, or 3 above the mean, -1, -2, -3. If you go below the mean, so it looks like this. This one up here, it has the 1, 2, 3. So this is 1 standard deviation above the mean, 2. Or a z-score, you know, you might have 0.5. That means it would be 0.5 standard deviations above the mean. Or negative 1.75 is negative 1.75 below the mean. So you just use that formula to convert, and then we'll talk about like an application problem. I will mention on the slideshow, if your data value is your mean, your z-score is 0. If your data value is to the right of the mean, your z-score will be bigger than 0. And if your data value is to the left of the mean, it's less than your mean, your z-score will be less than 0, will be negative. So z-scores can be positive and negative. Generally, your data values, when we talk about application problems, they're always positive values because we're talking about scores or amount of time it takes or whatever that deals with positive units. But z-scores, if they're negative, that just means your data value is to the left of the mean. It's below the mean. So your z-scores can be negative. So to convert, we want to calculate the z-score here. The amount of time it takes for the pizza delivery is approximately normally distributed with a mean of 25, so there's my mu, and a standard deviation of 2. And if you want to draw a picture for this, you can. This we're only converting using the formula, so I'm not going to bother with it this time. Convert 21 minutes into a z-score. So we do z equals, this is our formula that we use, 21 is our x. So we do 21 minus our mean of 25 divided by our standard deviation of 2. And z should be negative because 21 is below the mean, so z will be negative. So this gives me -4 divided by 2, which is -2. And you can, I said I wasn't going to draw it, but I think I will. I can hold my paper still. So just for this one, your mean is 25 here. This is for x. And for z, it would be 0. Now the curve, it'll be spread out different from standard normal to just any curve. But just so you can see here, x would be 25 on this row. Z is 0, 1, 2, 3, or decimals there. So if you want to know about 21, if you go 1 standard deviation below the mean, 25 minus 2 is 23. Minus 2 again, 2 standard deviations below puts you at 21. So for z, we'd be at -1, -2. So there you can kind of see how they're corresponding. And then of course you can always have decimals as well. If you want to convert 29.7, that's our x now. So we want to do 29.7 minus our mean of 25 still, divided by standard deviation of 2, and we'll get 4.7 divided by 2, which is 2.35. So you could go up if you wanted. If you go 1 standard deviation above, 25 plus 2 is, 25 plus 2, 27, and here's 29. Z would be 1, 2, and then you'd go up 2. you'd hit 31. That would be z of 3. I should have moved my x and z over, but 29.7 is here, so you know it should be 2 point something because 29 is 2, is the z, corresponding z score is 2, so 29.7 should be 2 point something, so it's 2.35. For z scores, you always round to 2 decimals. You can also go the other way. You can, so that's just using the z-score formula. But you can also go the other direction. You have what's called a raw score, which is the result of converting from your standard units, which is your z-scores, back to your original measurements, your original x values. Using the formula is x equals z times sigma plus mu. You get that because if you do your z-score formula to solve for x, that's what we're trying to do, multiply both sides by sigma, we get z sigma, draw an arrow instead, is equal to x minus mu, and then add mu to both sides. You get x equals z times sigma plus mu. So you can solve one formula for the other. So if you want to interpret a z-score of 1.6, if there's a mean delivery time of 25 and the standard deviation of 2, same kind of problem. So this is going the other direction. It gives you the z-score. You want to find x. Then we would use this formula. X is equal to z, which it says is 1.6, times sigma, which we know is 2, plus our mean of 25, and we get 28.2 minutes. Which makes sense because if you look here for z-score of 1.6, if I go back to my picture here, z of 1.6 is between 1 and 2 here, be somewhere right in here. So it should be between 27 and 29, and it's 28.2, so that makes sense. So the purpose of doing z-scores is so that you can calculate probabilities. Probabilities using the table, which there's a table posted, or you can use the calculator. Most people choose the table on this one just because the calculator is a little bit finicky on exactly what you have to type in sometimes. So generally, to find the probability, most people just use the table. So it's up to you. I'll show you both ways. So I'm going to show you the pictures on the PowerPoint real quick. So to do the probability table, if you can see that okay, the table is always to the left of z. So the probability listed in the table is always what's to the left of z. So it's not to the right, but it's always to the left. So if you want to find the area to the left, then you just use the table. If you want to find the area, that was a negative. I think that's a negative. Yeah. You use the table. If you want to find the area to the left of a positive z, still just use the table. If you want to find the area to the right, so one like this, the total area under your standard normal curve is 1. So the table only gives you what's the areas to the left. So if you want to know what's to the right, you take 1 minus, so take the whole area minus whatever's to the left. So 1 minus the value from the table, that gives you the area to the left. I mean the area to the right, sorry. And then if you want to find the area between two z values, here's what you want to find. The table, if you look up z2, it'll give you all of this. So you find the area to the left of z2, and then you just need to take off this little piece down here, whatever's to the left of z1, that leaves you with what's in the middle. So you take the area, whatever's in your table of the bigger z value, subtract off the area of whatever's in your table of the smaller z value, and that leaves you with the area between them. So an example, table A2 is referring to the textbook, the Triola book that I use just to pull examples from and stuff, so that's why it says table A2. Yours doesn't have an A2 on it, but anyways, it's the same chart. So we want to find the probability that z is less than 1.27. So I have the chart printed here. This is the negative side, and then here's the positive side. So for 1.27, if I can get it all in the thing here, you go positive side, go down to 1.2. Here's our z value. go over to 0.07. Whoops, missed it. And you should be here at 0.8980, and that's your probability. So this is 0.8980. So the chart is super easy. That's all you have to do. If you wanted to use the calculator, just so you can see, a calculator may give you a different decimal on the end, but what you do to do it on the calculator, you hit second vars, go to normal CDF, and this is on the last page too. You need to type in a lower bound first, so you need to just use some big number. So negative 1,000 usually works. Some people say negative 10,000, but I've never had an issue with negative 1,000. And then you type in your whatever your Z, or the calculator can handle X's. You don't have to convert to Z's, but your Z 1.27. And then you type in your mean. So that's why the calculator can handle X values, because you can type in different means. It doesn't have to be the 0 and 1 for your mean and standard deviation. But if it's a Z, your mean is 0, and then you type in the standard deviation, which is 1. And you get 0.89795, which rounds to 0.8980, because for probabilities, you always round to 4 decimals. So Z-scores round to 2 decimals, probabilities round to 4 decimals. But this is a lot, excuse me, to type in, and it's a lot to remember because you have to put a lower bound, upper bound, mean, standard deviation. So you have to do it that way every time. If you're looking for the area to the left, you can go all the way to negative 1,000 is fine. So most people, that's why they just elect to choose to do the chart, because they can't remember what all to type in here. But that's how you can do it on the calculator. Oh, and there I have it highlighted in red so you can see. So find the area to the left of negative 1.65. Same thing. There's the table on here. I can do it on the sheet here. You want negative this time, so go to the negative side, negative 1.65. So go down to negative 1.6. This is why Z-scores are always 2. Over to 0.05, put you here. So you're at 0.0495. And the area to the left is the same thing as Z being less than negative 1.65. For your any value smaller than negative 3.49, that's as small as it goes, you just use 0.0001. Anything bigger than 3.49, I've never actually seen anything bigger, because it's almost all the data values are within 3 standard deviations, so you can use 0.9999. So if there's anything smaller or bigger than the end of your table, you just use 0.9999 or 0.0001. But you won't see that, I don't think. So if you want to do the probability that Z is less than 1.64, that's just using the table. Go to 1.6 over to 0.04, you're at 0.9495. And again, you can do it on the calculator, but most people like the chart, so I'm just going to go with the chart. If you have calculator questions, just let me know. Less than negative 2.71. Go to negative 2.7, which is up here, over to 0.01, you're at 0.0034. Now if you want between two values, so here, this is one where you can use the calculator or you can use the chart. You just have to remember what to subtract. If you want to use the calculator, you still do second vars normal CDF, but if you're between two Z values this time, you got 0 and 1.24. So we have a lower bound of 0. Your upper bound is 1.24. Your mean of standard normal for Z-scores is still 0, and your standard deviation is still 1. So the calculator will give you that one, and you don't have to remember to subtract. So some people do use a combination of both things. It's totally up to you. I don't care if you want to use the chart or if you want to use the calculator. To do it on the chart, I'll just sketch this one real quick. So So we want between 0, which is in the middle or mean, and 1.24, which is here, we'll say. Oh, that's supposed to be in the middle. Really not very good at drawing these, but good enough. So we want what's in here. So if you just ignore this for a second, you shouldn't have to use the chart if you ever want to know the probability that z is less than 0 or greater than 0, because the chart's symmetrical. The area under the curve is 1. So if you cut it right in half, this side's 0.5 and that side's 0.5, just as a side note. But we want the area here. The chart will tell us to the left of 1.24, so it'll tell us all of this. So we take that value and subtract off, we need to subtract off the area to the left of 0, and that leaves us with this little open area here, which is what we want. So if we go to our chart and do 1.24, so we go to 1.2 over to 0.04, 0.8925. Minus to the left of 0, I just said if you cut the chart in half, it's a half, 0.5 and 0.5. You can verify 0, 0 is up here, 0.5. And subtract those, you get 0.3925, which is what the calculator said. So for the chart to do between, you just have to remember, take the bigger z value, subtract off the smaller, or the probability for the bigger z value, subtract off the smaller one, and then that leaves you with what's in the middle. So for this one, we have between negative 2.37 and 0. So again, we're going to be over here, this is over here is negative 2.37, so we want between them. So we take whatever's to the left of 0, which we just said was 0.5, minus whatever's to the left of negative 2.37. So go to negative 2.3 over to 0.07, gives you 0.0089. And subtract those and you get 0.4911. Between negative 3 and 3, well, if you think about the empirical rule that says it's almost all the data, or 99.7%, is within 3 standard deviations, you should get 0.997. Probabilities are always rounded to 4, so if you just wrote down 0.997, I would give it to you. If you thought about that, most time people don't think about it, they just keep going. So we want what's between negative 3 and 3, so again, it would look like this. Take off, do the chart value for 3, subtract off the value for negative 3. So if we look up the value for 3 here, we get 0.9987 for 3.0. Minus the value for negative 3, which is up here. Negative 3.0 is 0.0013. And if you subtract, you get 0.9974, which is 99.7%. If you round to 3 decimal 0.997. So that one, if you wrote down 0.997 because you thought about the empirical rule, I would take it. Between negative 2.34 and 1.57, I think I probably showed you enough on how to do the chart, how to look it up. Go to 1.57, should give you, assuming that I looked at the right number before when I was doing this, 0.9418. If any of these are wrong, you can let me know and I'll fix it. Minus, if you look up the value for negative 2.34, you should be at 0.0096, and you'll subtract those and you get 0.9322. Between negative 2.44 and negative 0.73, again, go to the value for negative 0.73 on your chart. Should be 0.2327. Minus, go to the value for negative 2.44 on your chart. Should be 0.0073. And that equals 0.2254. We haven't done to the right yet, greater than or to the right. If you want the probability that z is greater than 2.39, let me draw this one. So here's 0 and up here's 2.39. And we want the to the right. So again, you can use the calculator if you want. If you want to do it on the calculator, if you want the area to the right, the calculator can go right or left, it doesn't care. Area to the right, you type in your lower bound. So we got 2.39. Your upper bound, instead of using a negative 1,000 for a lower bound, we're going to use 1,000 for our upper bound, or 10,000 if you feel more comfortable. Mean for standard is still 0, standard deviation is still 1. So you get 0.0084. So you can also do that on the calculator if you choose. To do it on the chart tells you this part here. And the whole area under the whole curve is 1. So we're going to take away 1 minus whatever the value on the chart is. So 1 minus, I'll just do this one on the chart, 2.39. There's 2.3 all the way over to 0.9, here, 0.9916. And if you subtract, you get 0.0084, which is also what we got on the calculator. So if it's to the right, you just take 1 minus whatever the chart value says, or you can do it on the calculator if you choose. So for greater than negative 1.43, same thing. We're going to do 1 minus whatever's to the left. So look up the value for negative 1.43. Should be 0.0764, which is equal to, if you subtract that from 1.9236. So that's just how to use the chart or calculator. I'll showed you how to do it on the calculator too, just so you know. So for an application problem, the amount of time it takes still for the pizza delivery is normally distributed with a mean of 25. So there's our mean. Standard deviation of 2 still. If you order a pizza, find the probability that the delivery time will be, excuse me, between 25 and 27 minutes. So if you were to draw this, so mean of 25, if you go 1 standard deviation above, you're at 27. So for Z, that would be a 0 and 1 correspondence. So that one's kind of easy for Z. If you don't notice that, you can always calculate a Z. You would have your first one would be 25 minus 25 divided by your standard deviation. That would be 0. Your second Z would be 27 minus 25 divided by your standard deviation, which would be 1. So the probability that X is between 25 and 27 is the same. Oh, sorry. As Z being between 0 and 1. So if you look up, oh, got a tickle in my throat. If you look up the value on the chart for 1, subtract off the value for 0, and you'll get 0.3413. Oh, goodness. Okay, just writing here so you can kind of follow along. So 22.7, if you want less than that, it's probability that X is 22.7 is less than 22.7, so calculate your Z, still using the same formula. you get negative 1.15. And you can look up that value on the chart. So you should get 0.1251.